Welcome to the fourth lecture in our seventh week of our course, Analysis of a Complex Kind. This lecture will focus on new tricks to find residues. Now that we have the powerful residue theorem, we need new techniques to find residues more easily. Let me remind you of the residue theorem. Suppose f is a function that is analytic except for an isolated singularity. So that means f is analytic in a punctured disk centered at C0 with the exception of C0. In that case, f has a Laurent series representation in that punctured disk, which is a doubly infinite series of terms ak, these are the coefficients, times z minus z0 to the k, where k runs from negative infinity to positive infinity. We say the residue of f at c0 is the a minus 1 term. This is the term for which k is equal to minus 1, and that is the coefficient of the 1 over z minus z0 term. Let's start by finding residues at removable singularities. Recall that a removable singularity is a singularity for which you find out that after finding the Laurent series, there are actually no terms that have negative powers of z minus z0. So all the ak's are actually equal to 0 for k less than 0. Well, in particular, then a minus 1 must be equal to 0, which is the residue. So in that case, the residue of f at c0 is 0. Let's look at an example. The function sine z over z. Sine z over z has an isolated singularity at the origin because that's where we're dividing by 0. Otherwise, the function is analytic. Sine z itself has a Taylor series representation centered at the origin, namely z minus z cubed over 3 factorial plus z to the 5th over 5 factorial and so forth, that you see right here. If I divide that by z, I find myself with 1 minus 1 over 3 factorial times z squared plus 1 over 5 factorial times z to the 4th, and so forth. That's the Laurent series representation of sine z over z, which we use to show that z equals 0 is actually a removable singularity for this function f. Therefore, the residue of f at 0 is equal to 0. Next, let's consider residues at simple poles. Recall that z0 is a simple pole if the a minus 1 term in the Laurent series representation is non-zero, but all other ak's for k's less than negative 1 are equal to 0. So there's exactly one negative power of z minus z0 in the Laurent series expansion. So f has the form a minus 1 divided by z minus z0, and then all non-negative powers of z minus z0. How do we find this a minus 1 term? Here's the idea. We multiply through by z minus z0. If we multiply both sides of the equation by z minus z0, we find that z minus z0 times f of z is z minus z0 times a minus 1 over z minus z0, so that's just a minus 1. And then each term gets an additional z minus z0, so a0 times z minus z0, a1 times z minus z0 squared, and so forth. Now if I let z approach c0 and take the limit, then as z approaches c0, this term goes away, this term goes away, and all I'm left with is this term right here. So the residue of f at c0 can be found by taking the limit as z approaches c0 of z minus c0 times f of z. Let's see if we can use that in an example. Let's look at f of z equals 1 over z squared plus 1. We've already looked at this function before. We know it has simple poles at z0 equals I and z0 equals negative I. We'll focus on I right now and try to find the residue at z0 equals I. By our formula, we can find that residue by first multiplying the function f by z minus I. That's what you see right here. We multiply f by z minus I. And then we need to take the limit as z approaches I. But 1 over z squared plus 1 is actually equal to 1 over z minus I times z plus I, because we can factor the denominator. The z minus I in the denominator cancels out with this z minus I, so that we're left with simply 1 over z plus I. The limit as z approaches I of that fraction can be found easily by simply plugging in I for z. And if I plug in I for z, I get 1 over 2i. And 1 over 2i is the same thing as negative I over 2. So the residue of this function at I is negative I over 2. That's the same residue we found last class with a very different method. Next, let's look at double poles. A double pole is one for which the a minus 2 term is non-zero, but all further ak's for k less than or equal to -3 are equal to 0. So f has the form a minus 2 over z minus z0 squared. Then maybe there's an a minus 1 term, or maybe not. And then all the rest of the terms are non-negative powers of z minus z0. How do we isolate a negative 1? The idea is very similar. This time we multiply through by z minus z0 squared, the largest denominator we have. So z minus z0 squared times f of z gives us simply a minus 2. And the a minus 1 term gets an extra z minus z0. a0 gets a z minus z0 squared, and so forth. We can't simply let z approach z0, because if we did that, we would isolate a negative 2. But we're not interested in a negative 2. We're interested in a negative 1. That's why we have an additional trick right here. We take a derivative. If we take a derivative of this equation, then the a minus 2 term goes away. We're left with an a minus 1 term. The derivative of a0 times z minus z0 squared is 2a0 times z minus z0, and all the subsequent terms have some power of z minus z0 in it. Now, if we let z approach z0, all these subsequent terms go away, and we're left with a negative 1. So we found our formula for double poles. The residue at the double pole can be found by first multiplying the function by z minus z0 squared, and then taking a derivative, and then taking the limit as z approaches z0. Let's look at an example. Let's look at f of z equals 1 over z minus 1 squared times z minus 3. That function has a double pole at z0 equals 1. It also has a simple pole at 3, but we're not interested in that pole right now. We want to find the residue of f at 1. By our formula, we need to multiply this function by z minus 1 squared. That's what's happening right here. Then we need to take a derivative, and finally the limit as z approaches 1. We see right away multiplying by z minus 1 squared is very convenient, because the z minus 1 squared term will simply cancel out, so that we're left with having to find the derivative of 1 over z minus 3, and then the limit as z approaches 1. But the derivative of 1 over z minus 3 is minus 1 over z minus 3 squared, and the limit of that as z approaches 1, we simply have to plug in 1 for z. 1 minus 3 is negative 2. Negative 2 squared is 4. And so that the residue of our function at 1 is negative 1/4. Let's try to generalize these ideas. Suppose now we're dealing with a pole of order n. That means the a minus n term is non-zero, and all other ak's for k less than or equal to negative n plus 1, those are equal to 0. So my function looks like this. I have a minus n over z minus z0 to the n, and then terms with the denominator gets better and better, all the way through a minus 1 over z minus z0, and then the non-negative powers of z minus z0. The idea is the same thing. We're going to multiply through by z minus z0 to the n, and if I do that, I'm left with a minus n plus a minus n plus 1 times z minus z0, all the way through a minus 1 times z minus z0 to the n minus 1, plus a0 times z minus z0 to the n, and so forth. I want to isolate the a minus 1 term. So I can't simply let z approach z0. I need to isolate this term, and therefore I need to take an n minus 1-fold derivative. If I take a derivative n minus 1 times, this z minus z0 to the n minus 1 will go away. All these terms in the front will also go away under differentiation, and only terms to the right will be left. So if I differentiate this n minus 1 times, I find the following. The first time I take the derivative of the a minus 1 term, I get the n minus 1 from the exponent, then an a minus 1 times z minus z0 to the n minus 2. The next time I differentiate, I get the factor n minus 2 up front, and so forth. If I differentiate n minus 1 times, the z minus z0 term is gone entirely, and I have an n minus 1 times n minus 2 times n minus 3, and so forth, all the way down to 1 times a minus 1 term left. The a0 term also has all kinds of things up front here, but it has a z minus z0 term left, and so do all the subsequent terms. Now, if I let z approach z0, all these subsequent terms will go away. So if I now take a limit as z approaches c0, then I can isolate my I-1 term if I simply divide by this number right here, which happens to be n-1 factorial. So we just found the following formula. The residue of f at a pole of order n is 1 over n-1 factorial times the limit as z approaches c0 of the n-1-fold derivative of z minus c0 to the n times f of z. This formula clearly contains the two cases that we already considered earlier, the simple pole and the double pole, but now you can use it for higher order poles as well. To finish, I want to show you one other very useful little fact. Suppose you have a function f that is a quotient of two analytic functions, g and h. For h, the denominator has a simple 0 at c0. Then the residue of f at c0 can simply be found by taking g, the numerator function evaluated at c0, and dividing that by the denominator derivative at c0. Let's get back to the example that we looked at when we looked at a double pole. F of z equals 1 over z minus 1 squared z minus 3 has a double pole at 1, but also a simple pole at 3. This time we want to find the residue at 3. We can look at this function as the function 1 over z minus 1 squared divided by the function z minus 3. The function g, which is 1 over z minus 1 squared, has an isolated singularity at 1, but is otherwise analytic. So in particular, near 3, it's very much analytic. For example, if I look at a little disk around 3, in that disk, the function g is entirely analytic. The function h of z, which is z minus 3, is also analytic. It's analytic everywhere and has a simple 0 at 3. By the fact, we can therefore find the residue of the function f, which is g divided by h, by simply plugging in 3 into g and plugging in 3 into the derivative of h. While g of 3 is 1 over 3 minus 1 squared, 3 minus 1 is negative 2. Square that, you get 4, so this is 1/4. And h prime of 3 is equal to 1 because the derivative of h is simply equal to 1 everywhere. Therefore, the residue of this function f at c0 is 1/4. We could have just as well found the residue of f using the fact that 3 is a simple pole, and we could have applied that formula. The calculation would have been quite similar. This is just another way of finding residues. In the next lecture, we'll use the residue theorem to find some interesting integrals.